Hello everyone. In this session, we are going to discuss about a project which is going to be next word prediction using LSTM architecture. So in the previous sessions, we have discussed about wide variety of pre-processing techniques, some advanced way of pre-processing as well. Then into deep learning, some basic architectures like artificial neural network. Then the advanced version of it, something like LSTM, RNN, LSTM, and their advantages we have discussed, and we'll be implementing those in this particular project where we are going to utilize LSTM for the prediction of the next word. And this could be like a next word suggester in a lot of applications we are using nowadays, right? So in mobile phones, in WhatsApp, where you start typing, you have the upcoming word suggestions. This could be your possibility. So if you type a mail, they also have it there itself. When you try to do some search in Google, it will also pop it up. And if you are fine with it, if you press tab or some denoted key, they will be just pasting it. You don't want to type it. So these are actually utilized with the help of LSTM or NLP techniques, and we will be utilizing LSTM to achieve that, to predict what is going to be the next word based on the context you are having now. And for this particular process, let us see an introduction. So predicting a next word using LSTM has been an area of research and used widely in different applications. And predicting the next word is a neural application that uses RNNs. Basically, we know that RNN has some problems. So advanced version of, once again, LSTM is again RNN. The basic RNN we are not going to go with it. We will be proceeding with LSTM. Even though the RNN has some flaws, it has been overcome in the help of LSTM. And what we are trying to do here is the task, which is something like if you have the context, then you want to have the particular next word suggesting based on the context. Based on the previous words in the context, we will be predicting what could be the next word. Here, any of these could be okay. Maybe books will be very optimal. Apart from that, if you have something like the students opened there, and then if you have something like some other word which is not relevant, then that is wrong, right? So we need to make a prediction which is accurate as well as based on the context as well. And talking about the data set, we are going to use a data set which is actually from the Project Gutenberg of ebooks. They have a wide variety of, they are an organization who is doing this open source conversion from the physical books into ebooks, digitalization process. And the Project Gutenberg ebook of Metamorphosis. Okay, so there's a book called as Metamorphosis. It serves as an invaluable data set for various NLP process. It's open source. It includes, we will be utilizing it for text prediction. It was written by Franz Kafka, and this literary masterpiece is free, open source, offers rich and diverse linguistic patterns, and making it an ideal resource for the training of large language or training the language models. It is not only used here, it is used in variety of NLP tasks like training for LLM, and for some other NLP applications it is preferred. And there is a site also where we could actually view it, and we could also get it. Let us view it. So this is, if you click the new link, it will be taking you to this place. We have it as a text file, so we'll be utilizing that to load and make predictions. So it's likely we have some things happening here. It's like a story, it is going on digitalized format, but we will be storing it in a text file and then utilizing it for our particular process. And the process or the steps which we will be following in this will be data collection, exploratory data analysis, pre-processing, vectorization, padding, LSTM, and then inference as well. So this is going to be the steps, and let us kickstart now by going into our Google Colab, where first let us load the data set. And let us start with importing the required libraries as we used to do. So we'll be utilizing TensorFlow library for creating the LSTM and neural network. So first let us import TensorFlow as TF, and from TensorFlow dot keras dot preprocessing dot text. So we know that we will be like if you want to convert your text into vectors or new meaningful numerical representation, we have seen variety of tools: bag of words, TF, IDF, word to vec recently. So the word to vector is a concept. Okay, you can use it with Gensum, or you can also use some other tools from the TensorFlow. For that, we will be utilizing a layer called as embedding layer. We'll be discussing about it. And before that, we will be making it into token. So that is, you can also create your own, or you can utilize this TensorFlow's tokenizer, where if you pass a text, it will return you a number. So it has its own dictionary kind of format where it returns the tokens, so that later on you can use it for its training. It will be turning them into numbers. So we'll be importing tokenizer. It is actually from the pre-processing of text from the TensorFlow Keras, and then going into creation of neural network, we will be requiring TensorFlow, Keras, layers. We'll be importing embedding layer, LSTM, and then dense layer as well. So here embedding layer is what we are discussed. I'll explain when we go and implement it. Especially when we do word to vec, we have done it in various ways. We have done it hands-on as well. So similarly, this Gensum, if you use it, is already pre-trained on a different data set. You could adapt it and then retrain on your own. It's like fine-tuning. But also when you create your neural network for this particular data, you can also add a single layer which is embedding. It will take care of that. Okay, whatever the word to vec is doing for this particular data you are passing, this embedding layer will be absolutely taking care of it. It will do the same thing, as we know that it uses continuous bag of words to predict the next word, so that it can understand and give its meaningful numerical values in the vector space, like the king, queen, man, women. We have discussed about it, I hope so. And LSTM is the LSTM layer, and we have the dense layer going on here. So this is a hidden layer for hidden layer tasks. And from TensorFlow dot Keras dot models, we'll be importing sequential, and see, this sequential is a place where we will be adding all the layers. It's like combining everything into a stack, so that all the layers can be turned into a model to make the workflow for backpropagation and all. So from TensorFlow dot Keras dot utils, we need something known as to categorical here. So if you want, you could use pandas or any other tools manually, you can do, or you can use this categorical as well, since if you are using a neural network with TensorFlow, it is better to go with what all things they have defined in such way that all the dependency issues won't be popping up. It will be smoother for us. So we may need NumPy, and we'll be requiring Pickle. Pickle is actually a particular library. It is used in machine learning and deep learning, where particularly what you will be doing is you will be making them into like if you have a model, if you trained it, you can save that model so that later on we can just use it. And compare the task with machine learning. Machine learning we have done with just few seconds, it will just complete it. But that's not the case with deep learning. In deep learning, with the complexity increases, the epoch increases, the time consumed will be very more, and that is a difficult task, and every time you can't retrain and make prediction. So once you train it, if it's fine, you can save it. That will be using Pickle and all. And not only for that, if you have some other, like if you want to store some other properties like the tokenizer, or if you have a scalar, if you want to scale it and then you want to save its all the functions inside, you could use Pickle to export it. So this is enough. Let us run this, and let us go and pick our data set now. So we have a data set which is of text file format. Let us refresh it. So we have it as a text file. Let us copy the path of it, and let us run something like, for example, files is equal to, let us use open option, and we'll go with text file, the name of it, and then what is the way you want to read it as read, and then the encoding I'm going to perform here is UTF-8, the common encoding. And then let me get all the lines. So lines equal to a list, and for all the lines for I in files, it is going to open one by one. You can iterate it, and I'll be just appending it. So I'll be adding lines dot append of I, and this will make sure that all your lines are inside this. So now let us make a view of it. We'll be having a bunch of lines. Now we have sentence tokenized, and you can see since it is actually from a different maybe something like text file, you have the new line character, some other details which is especially a lot of details are unnecessarily present. May have to do some pre-processing. You can see that it is starting, maybe it's some tag in the start, we'll be removing it, and we have all the sentences available. That's a good sign. And just to make sure how many we have, let us run something like the length of lines. How many sentences do we have here? It's 1946. Such a good piece of literature for us to work with. So we'll do the basic pre-processing now. So the data is equal to, I'll create it into a paragraph now. So for I in lines, we can go over the data is equal to, leave a space and then dot join. This is to combine, and you can pass the lines inside, and for every line it is just going to combine them, and then what we'll be doing is this will keep on running so that you get a paragraph. So in that totally I'll be adding something like dot replace. So we had that new line character, right? So I don't want that new line, I want it to be replaced it into empty. And then you can use another replace, something like if you want you can replace the rastering. If you have, just remove it and then dot replace, and here we will be passing that particular starting sign UE UF EFF, and then I'll turn it into nothing once again. And yeah, so I hope we can run this and do the process. Yeah. So now if you look at that data, and maybe something like I look at the first 500 words, and this is what the processed words are. It looks okay. We could just use it for making the process. And yeah, so now we could move into the next steps where we'll be doing some other things like removing punctuations or other processes. So for that, let me just go and import string, and we will be doing something like a translator. So the translator is equal to string dot make trans, and you can call the string dot punctuation. You could use replace, or you could use this method punctuation, and then I'll just leave it like create spaces based on the length of string dot punctuation. And you could call the new data is equal to data dot translate. Could pass the translator. It's a string method, it will be doing the process now. So the new data of the first 300 words, we'll look into it. So this is what it has removed the punctuation. So how many punctuations you had, it will leave that many spaces. That's why we multiply that. So it has done the process. Now it's our next step to proceed with other details, such as, for example, let us run, like we'll create a new list again, and we are going to do like for I in our data dot split. Okay, and we can do something like if I not in new, then we can go with new dot append of I. So this is to make a copy of all the uniques, and once it is done, okay, I in data dot split, and you have to pass this. And apart from that, once it is done, we can also go with data equal to, like we can create, we had our new data which is pre-processed. Here we'll just join this and create our data back, and this will give us some of the words which are uniques in the format in that particular places maybe. And once this is done, we can go and process with the next steps of tokenizing and making the process. This is for our purpose, and then we'll create the tokenizer, which is new for us. So first I'll create an object for this tokenizer. So that is equal to the tokenizer. And once you had this tokenizer, first we can fit on texts. Okay. So calling this to fit underscore on underscore texts. And I'll be passing this data. Why? Because this tokenizer, we will be doing all the tokens, and we had all the unique words here. And we'll make a tokenization of it, so that we don't want it to repeat, right? So we get this, and then we can apply this on the new set of data and go on. So first let us fit it here. Fit on texts. It is texts. Yeah. Now it will do the process. Yeah, so the tokenizer has been fitted, and for saving this tokenizer, if you want to use this tokenizer to get the same context, you could use pickle, which we have imported. You could call dump, and you have to tell what you are dumping or what you are storing. I am storing tokenizer. Then what is the file you are going to store? Create tokenizer .pkl is the extension, and I want it to write binary format. And let us run this to save it actually. So we'll be getting it here. Now the tokenizer.pkl, please make it download and keep it for your later reference. It can be used later on. So let us download it. It will be downloading soon. Fine. And proceeding further, now it's time for us to proceed further where we can create sequences now. So let us go with sequence underscore data is equal to create a sequence. You can go and call tokenizer dot texts to sequences. So it will create, once it has been fitted, now if you pass text, it will be turning them into sequences, and we'll go and pass the data inside. And if you do it, you will be getting the additionals as well, like in a 2D. So you get the 0th index, so you get the tokenized result. Maybe if you look at the sequence data and look at the first 10 maybe for now, so you'll be getting numerical representation which tell that that particular word where it has been located, especially you will be getting that. And if this is the text, then our vocabulary size, we'll be needing it later, and the vocabulary size will be something like what's the length of your word index. So word index is something like, if you go and call this tokenizer dot word underscore index, you get all the respective details, which is what all the words and what is the number has been given. It's like bag of words, right? So you are just making a count of it. So you get this, and please make sure that the vocabulary size always will be the word context plus 1. That's how it will be given. So that is your total vocabulary size. And so you have nearly around 2617 words here. And then what we are going to do is we are going to now create sequences. So now we have our words, but this is a next word predictor. So that text, or we have just a bunch of paragraphs. The features here is going to be text, and the target will be the next word. You will be just having 3 words, and the next word, 4th word will be the target. So the next set 3 word, and the next 4th word will be the target. We keep this window moving on like in continuous bag of words, so that it can learn to predict the next word. So for that, we create some n-grams on our own. So for I in range of 1 comma the length of sequence data, so it will run till that. So our sequence data is there, so you have all the numerical representation of your text, and the words is equal to, you call the sequence data and you can slice it actually. So do something like I minus 1, which means your value starts from 1. So when this starts from 1 comma the length of your sequence data, so maybe something like, if I run it, what's the length of my sequence data totally? Okay, it will run till that, and you start from that, okay, 0, and then you are going to slice it till I plus 1, and that's the length. So you are getting something like, if you pass 1 here, it is 0 is to 2. So you get first 2 word as the word, and you can append it. So you are just storing like this, next, you are doing it. And the sequences dot append, let us pass the words inside. And if we look at the sequences of maybe first 10, so this is a sequence we had 17 and 53, the first 2 words, then the next is 53 and 293, then the 293 and 2, then 2 and 18, the sequence 2 2. So if you want to increase the window size, maybe you want to give 3 words and predict the next, you can go and increase this to plus 2, so it will have 3 words. So in that manner we could pick it. And what we are going to do next is we will be just creating sequences is equal to np dot array of sequences. Okay, so we create an array of sequences now, and what we'll be doing is let us perform something like, for example, let us go and do x is equal to empty list, y equal to empty list, and for I in sequences, okay, so we will be calling x to append I of 0. Okay, so 0th one will be the feature, and the next word will be the target. So if 17, then it should be 53. If 53, the next should be 293. So in such way, we are going to train it. So y dot append, it is going to be one word and the next word. If you want to increase the context, you can go and increase as well. X and y in this manner, we'll go with it. And now if we run it, it is going to do the process for us. It will be appended. And if you look at X and if you look at Y, that will give us the respective result. Okay, it is I of 1, that's the issue. So you go with I of 0 here, I of 1 here. So the first word will be the feature and the target is going to be the next word. And looking into X, you have a sequence and Y will be one step next. So that's why we have went in that way. So okay, isn't it an array? So we can even turn it X equal to np dot array of X and Y equal to np dot array of Y, so that we can see it as array and see the differences. So we'll just print the value X here and then the Y here after array conversion. So this is our features 17, 53 and the respective. For 17 it's 53, for 53 is 293, for 293 is the next word. In such manner we have this targets of next word will be predicted. It will run one step before, so after 591 here the last word, so that it matches. And finally Y, we need to make it as a categorical one because we want to predict categories, then we can use argmax. Otherwise it will be a regression problem. We wanted to make it as a classification of many classes, especially based on the vocabulary size. So the Y is equal to, you can use the two categorical which we have imported from the TensorFlow, two categorical, and you can pass your Y and the number of classes is equal to the vocabulary size, and this will do the process for us. And you will be getting it as now something like, if you go and see the first 10, you get it as a one hot representation as well. And you will be getting something like this where you get zeros and ones to tell which is present on that particular places. So like this we have obtained, and now it's time for us to move to the ultimate step, which is nothing but we want to create the model. So the model is equal to our neural network. So first create a sequential. This is where we'll be combining everything. So we will be having the sequential, and what we used to do is we will be adding layers to it. So now this sequential is like a stack. You can add lot of layers to it. So first I'm going to add. So using add, we will be adding the embedding layer. So that is our going to be the first layer here, because we have just a backup for representation. We need to use it to create vectors. Okay, so the embedding here is going to do the process similar to word2vec for our particular process here. So it trains on its own so that it do the process with itself. So here we will be passing the vocabulary size. So the input is what's your input and how many vectors you want to represent. I'll go with 100 for each word, and you go with input length. I'll be just storing this. I hope in this particular version there is no input length. In the older versions we will be having it. No issues, fine. Then we will be going towards the next step where we will be adding few more layers now. So starting with the next set of layer is our ultimate LSTM. So it's simple. LSTM, how many neurons you want to process. I want to extract here 1024. It's usually multiples of 8s are passed here. Usually people go with smaller size like 32, 64, 128 to 56, whatever they wish, and how much you increase, that many features will be extracted, the computation increases. And I'll just go with the return sequences. So just return me sequence as well. So if it is true, then you can connect it to the upcoming layers. If you don't want, then you can't go with it. If you want to connect it later on, you can go with it. Then I'll add another LSTM. So it's up to our wish. When we increase, the computation increases, the process increases. Maybe it can help or it can do overfitting. So it's under the process of optimization. So after these two, I'll add a dense layer now. So the dense is our hidden layers. I'll go with 1024 neurons and the activation. Here I'll apply a ReLU activation, because in LSTM we know we have sigmoid and tanh applied in various places on its own. That's the architecture of it. So finally I'll add my output layer. It's a multi-class classification kind of scenario. So I want to generate a vector size of my vocabulary size, and I want to perform activation of softmax so that I can decide who is the most probable. From that I can pick what is going to be my predicted word. And with this we are going to use something like model.summary. I'll create a summary of my model, and this is from sequential. So model is sequential, you get all the parameters which are included. So when you increase this value, the parameters changes, it increases the size and the complexity as well as the time taken. And before continuing, we'll be adding some additionals as well. So let us import some additionals from TensorFlow. Keras, you have something known as callbacks. You can import model checkpoint. So this is to generate checkpoints to store, and we can go with this. If you want, you can go and create the checkpoint. So the checkpoint is equal to call the model checkpoint. So which means if you even interrupt in between, you get to store the model file. So I'll store it as model of next word predictor.h5 is the extension of Keras or TensorFlow's file. And I'll just go with monitor the loss. And what you have to do is save best only, okay, is equal to true. And also we need to also tell it that don't show unnecessary details. For that, verbose is something like if you want to display information, you can adjust these values. If you go with higher value, you get lot of details displayed in the console. If you find it unnecessary, you can just drop it out, and this will do the process for us. And yeah, I hope these are enough. And what we are going to do now is we will be compiling. That's the important process. So while compiling, we need for example, we can go with model.compile, where we'll be passing who is the optimizer, and the optimizer is Adam, and the loss function is equal to categorical cross entropy. So since it's a multi-class classification, we can go with this. And then the ultimate and final step is to fit the model. So while doing that, you will be passing your x values, your y values, epochs, and one epoch is something like one forward and backward propagation of all your data. We'll go with the epochs of 75 for here. The higher the epoch, it will be better accuracy you get. We'll fit it to 100. We'll run it till 100, and I'll go with a batch size now. We'll go with a batch size of, for example, 64. It is also multiples of 8. Maybe I'll go with 128, which means for every batch, a batch is something like you pick some data and move forward and backward. If you go with batch size 128, then if you have 2000 rows, 128 details are taken forward, backward. So the next 128, forward, backward. Till that, it will complete all your 2000. Once it is completed, that marks one epoch. And the higher the batch size, faster will be the result. But if you go with smaller batch size, then your model can learn individual details, but it will take some time. And the callbacks here, you can go with checkpoint creations to store it. And now if you run it, if you don't get any error, all the process are smooth. And we got an error. Okay, we got some incompatible layer at the beginning. Maybe it's something like due to the input length which we have missed. Our input length is actually of shape 1. Maybe we'll try to add something like input underscore length is equal to 1 and run it. And it is better, like if you are having your model and if you run it 2 times, then it means that first you have a set of layer, now you had add another layer. So it is better to start freshly with the model so that it is kickstarting from fresh, which means earlier if you run it again and again, it means like you are stacking more layers below it. And if you go with summary, you get the sequential informations, and once again create your checkpoint details, compile it, and then fit it. Do we pass that error? Yes, we have successfully evaded that error. and let us go and wait for it to complete all the 100 epochs. So it is taking this much time to complete even one epoch, and the expected time is around it is taking more than 20 seconds, I hope so, totally. The reason is it is doing 31. You can see what is this 31. So it is seeing that you are having this verbose one telling some detail that from the beginning it is now best. So if you reduce it furthermore, it will save. It will save only when the loss is very less, means it will compare and save that. So finally you get a model which is very of low error, because error you can't always define that after every epoch. You can't tell it will reduce. Sometimes it will go up and all. So that we can save the best model here. And you can see what is this 31 is actually. So we have asked it to go with a batch size of 128, and if you multiply 128 with 31, for example, let us go with a calculator and do something like 128 multiplied by 31 will give you your total. So that is going to be the length of your data which we had earlier. We have gone with a vocabulary size, I hope so. So it is somewhere around here. We have precised it. So this is the length which tells that this much amount of like 128 you can't equally divide as well from 31, right? So it want to run 31 times so that it can pass 128 batches, 128 for the first, 128 for the next, so that it can complete one epoch. And let it run, and we'll come back when it completes all the 100 epoch. So after some time, all the 100 epoch has been completed, and you can see it is also telling you that from one particular point of time the loss has been improved. So when it improved, it is saving. Since it's the same name file, so you could get the same name replaced, so you don't run out of space as well. And typically here it's not loading anyway, so you can find it here. Leave it some time, you will be getting it. And one more thing is whenever if it is not that much improving, it is going to show you the respective detail as well. So when you go with verbose one, it tells that it's not improved and all. So to make an inference out of it, we'll create a function known as define predictive text, and we get a text inside. And once we get a text inside, what the user entered text, just pass it inside as a single word. What's the last word, just enter it. We want to predict the next word of the sequence. Get your tokenizer and convert from text to sequence, okay, because text to we need to get it back in sequence. And now it has been loaded, and I hope so this has been refreshed, and you get the model file here, which is every time if it improved, it is going to save in the same name, so it get replaced here. Make sure you download it so that later on, even if your internet cuts off or your kernel stops, you can just use it later. And yeah, it will prepare and get ready for download. So text to sequences, and you want to pass a text sequence, so pass it as a list and get the 0th, which is your array index. So go and convert it into array, okay, in p dot array of sequence. And then the predictions, just go and call your model to predict for this sequence. So you get output, and it gives you all the vocabulary size, but you want to predict who is the max, so you can go for argmax. So if you go for max, it picks the maximum probability. If you go for argmax in NumPy, it is going to take the index where the probability is maximum or the value is maximum, and the predicted word will be tokenizer. So you just call the index tokenizer dot index of the word and pass your predicted class. It will give you the respective word and return the word in word. You need to in the word format. And let us run this. And the final thing here is the text input. So the text is equal to get input from the user, enter text. So maybe the user is entering some text. So first I need to split it, because I have trained it for the last word, the next word. So just one word should be my input. Maybe he types 10 word. I'm not looking into the context. I'm looking the before word and then what's the next word would be. So I just need the final one. So first I'll split it into tokens, and in the spaces, let me split it. Even if you leave it, it is going to split in the spaces. And then let me just pick the last word alone. So I'll just go -1, it is a final word, and we'll just go with text equal to a string dot join of text, and we can go for just call this predictive text and pass our text inside. So this will pass and we should get the result back. Let us run this, and I hope here test text, right? So let us freshly run this back and run our text as well. So let it get the input. And do we made a mistake here? Okay, let us see. Predictive text is showing some error. Maybe there is some problems. We'll see. So the first thing we need to enter maybe something like screamed. Oh, okay. Predictive text is not defined. My mistake. Predictive text. Okay, here we are passing the text inside. We are splitting and getting the next word. Maybe if you pass with space. Again, input data shouldn't be empty. Okay, do we get any problem here? Especially we are splitting it, getting the input, picking the last word, joining it. Maybe here we just need to don't pass the empty text or the space inside at the beginning. So we'll go freshly and do the same input once again. Do we get output? Okay, screamed, oh god. I think it works well in that context, right? So someone is screaming, oh god, or something like that. We can try some other thing or next word as well. For example, let us do something like he found, and it takes the word found and then it predicts the next word. He found himself. Uh, Maybe something like we could try different. It takes the last word and predict the next word. Something like looked over. It works well. It works well after 100 epoch. The loss is around, the best loss is around 0.8. How much closer to zero it will be really great. And looking at from the beginning, it started from the loss of 7 and it has managed to reduce it under 1. And that's it about this particular project where we have tried to create a next word predictor using LSTM, which looks at the previous word and predicts the next word. And that's we have completed